Okay, we're going to look at another optimization problem here where we are going to try to maximize or minimize a function with a bunch of different information here. So we've got some information about a cost, a demand function, so P is price, X is number of pitchers. We are supposed to find the number of pitchers, so X, and the price, so that's our lowercase p, to maximize profit. Okay, so reading the problem, understanding that we are supposed to maximize profit and find maximum profit tells us that this is a maximum or minimum problem as opposed to some of the other kinds of word problems that we have done in this unit. And so we're going to just think about doing the problem the way that we have looked at these others. So first of all, we read the problem, identify what they want us to find. We do have several other things we need to give as answers. Number of pitchers, that's going to be X. And price, that's the lowercase p, in order to maximize profit and find that maximum profit. So I'm identifying those things. We now need to write down the function that we want to maximize. So I need a profit function. So in this problem, it's going to take us a few steps to get to that profit function. So first of all, we've been kind of doing this all semester in this course. So first of all, we have a cost, some information about cost. We have some information about revenue. And then we remember that profit is revenue minus cost. So you can skip some of these steps if you want, and you're not going to mess it up, but I'm going to go ahead and write these out here. So our cost function would be the cost per item. So her cost is $5 per item times the number of items. So 5x. That's her variable cost per item times the number of items. We don't have information about a fixed cost here. Sometimes we have that information for our cost function. Then we have a revenue function. Revenue is price times quantity. And sometimes the price is fixed. Perhaps we know that she's going to sell them for a fixed dollar amount per pitcher. Or sometimes it's variable. So this is a demand function where we've got a variable price per item. So here's our price, this function. Price per item times number of items. All right, so I'm going to simplify this since we're going to use it in some other calculations. So I'll distribute this x through 17x minus 0.5x squared. And then what we want to actually maximize is a profit function. So profit P, is revenue minus cost. So revenue minus cost. And I might notice I have some like terms here, so I'm going to go ahead and combine those. 17x minus 5x is 12x. And I'm going to go ahead and write the p of x down here because I will need to come back and grab this function. I'm going to put a little circle around this. It's not my answer, but because I'm going to need to use that in order to answer the question, I just want to be able to find it later. All right, so this is the function I want to maximize or minimize. When we talked through a process for solving word problems like this, optimization problems, we called that our objective function. So that's the function that we want to maximize or minimize. That's our objective. All right, in some problems we have constraints that we need to consider. So those might be things like we looked at some fencing problems where we only have a set number of yards of fence that we can use to enclose something, or some sort of restriction or constraints that we can use. We don't have any of those in this problem, so we don't have any constraints. Our objective function is just one single variable for the input, so we're okay on that for this problem. And then the next thing that we would want to consider is a feasible domain for the function. So I want to think about the values of x, the input values that make sense in the context of the problem. All right, so thinking about what x represents, it represents the number of pitchers that are made. So I can't have negative number of pitchers here, so x greater than or equal to 0 is our feasible domain. So that means if I get any x values in doing the calculus that are outside of this, I would just ignore them because they don't make sense in the context of the problem. All right, So once I've got my function that I want to optimize in terms of one variable, and I've thought about the values of x that make sense for that function, we're ready to now go to the actual calculus. So we're going to look for critical values, or critical numbers, or critical points. So that's where the derivative would be equal to 0 or not exist. So find the derivative, 12 minus, and then on this term, so I'll have minus 0.5 times 2 will be 1, so minus 1x. So a nice simple derivative there. So we want to think about where that derivative does not exist. That doesn't happen in this one. And then I want to think about where the derivative is equal to 0. So 0 is equal to 12 minus x, or x is equal to 12. My critical value, I want to make sure that that is in the feasible domain. It is greater than or equal to 0. If it were not, I would just ignore it for this problem. All right, and then I need to test to see if that critical value gives us a maximum value or a minimum value, or maybe neither. Sometimes our critical values give neither. So we talked about several different ways to test to determine whether this value gives us a maximum or a minimum, or maybe neither. So when we did local extrema, we did a number line, and we tested the signs of the derivative to determine where the function was increasing and where it was decreasing, and then that would tell us whether we had local maximum or minimum values. When we did absolute extrema of functions on closed and bounded intervals, we tested the output value at our critical values and then at endpoints of an interval, and we looked for the highest and lowest output value. And then another way that we haven't really done very much yet, but we talked about a little bit when we talked about second derivative, was to use the second derivative and concavity to test. So there are several different ways that you could test depending on what information is given. I don't have a closed and bounded interval here with two endpoints that my function makes sense on, so I'm not going to do the x, y thing. But I could look at signs of the first derivative, or I could use the second derivative. I'm going to do that just because I haven't done that in very many problems yet, just so you see an example of that. So I'm going to use the second derivative test. Remember that a second derivative tells you about concavity of a function, so whether the function is concave up or concave down. All right, so the second derivative here, I'm going to first of all find that. P double prime of x is -1. And when I use that second derivative test, what I want to look at is the second derivative evaluated at your critical number. In this case, I almost wrote f there, p double prime. In this case, when I plug in x equals 12 or any x value, I get the same value for my second derivative. But sometimes you have an x here, and so you put in that number for x. So it's -1. So what does that tell me? Second derivative is about concavity. So I know that this is a place where I might have a maximum or minimum value, and this tells me about concavity at that point. It tells us that the function is concave down at that point. And so at this point, I'm going to have a local maximum. So the maximum, if the function's concave down, and the critical point in that interval would be a high point on the graph. So that would be the location of a local maximum. All right, so that is where the maximum occurs. Remember, this was the x value, x equals 12 here. And so at this point, now I need to go ahead and answer the question. So this is where we're going to answer all these things that I underlined that it asked us to find here. So my advice is when you do these problems to sort of mark as you go through the problem what it's asking you to actually find. So x is number of pitchers. All right, so x is number of pitchers. Find the number of pitchers, so that's our answer. So x equals 12 pitchers. She should make, and the price she should charge for them. So I've got two p's in here, so paying attention to that. Little lowercase p is the price function. So that price when x equals 12, so 17 minus 0.5 times 12, so 0.5 times 12 is 6, 17 minus 60 is 11, so that's $11 is what she should charge. And then the other thing that it asked us to find was the maximum profit. So that's the profit function evaluated at x equals 12, when x is 12. So profit function evaluated at x equals 12, I circled this over here because I knew I was going to need to come back to it. So I'm going to evaluate my profit function when x is 12. So 12 times 12 minus 0.5 times 12 squared. So maybe you can do that in your head, or maybe you get out a calculator to do that, but you should get 72. 144 minus 72 is 72. And that is profit, so that would be dollars is her maximum profit. All right, and just making sense of your answers, the other thing that you could do is look at some graphs of these. You might notice that our profit function is a quadratic function with a negative coefficient on the x squared term. So that profit function is a parabola that opens down. So just in making sense of that problem, if you have a maximum value, that would be at the vertex of that parabola. So looking at that graph of that function and noticing the vertex of the parabola occurs at x equals 12. Here's our calculus work to verify that, but you could also look at that on a graph and maybe remember some algebra formulas to help you find a vertex of a parabola. All right, so the calculus wasn't hard here. The hardest thing, I think, is reading through the problem and being clear about everything that it's asking you to do, but I think just underlining can help, and being clear that what you're supposed to answer, and labeling your information here: cost, revenue, profit, maybe writing down some of those words if you don't remember what these letters mean. All right, try some homework problems.